So number 2, part D, this part said that if we cut the cord supporting the rod, so imagine that has been cut, you no longer are going to have a tension force. They wanted us to determine what the initial angular acceleration of the rod and block would be about the hinge. So when that happens, the rod's no longer in equilibrium. It's going to start to accelerate and rotate downward. This is our hinge. We have to use that as our pivot point because it is the actual physical pivot point. So we don't really care about the force from the hinge because it's not going to create any torque. We just have the weight of the rod and then the weight of the block. We no longer have tension, so just those two forces are creating torque here. And to get angular acceleration, we can just use the rotational form of Newton's second law. So we know that the net torque has to equal I alpha. And we're trying to find alpha. So I'm going to go ahead and rewrite that as angular acceleration will be the net torque divided by the rotational inertia of the whole rod block system. So net torque, we have our two forces creating torque. Each torque is RF sine theta. So for this force, its R would be 0.3 because that's how far it is from the pivot point. And then the strength of that force is 2 times 9.81 because it's just the gravitational force on the rod. And the force is perpendicular to the R vector, so we don't need to do the sine theta part. Then we also have the torque from the block. So its R is 0.6, the whole length of the rod, times its mass, 0.5 times 9.8. 9.8 is what I want to use there. And then, so that's net torque, adding the torques from those two forces. And then we just found in part C that the total rotational inertia of the rod and the block together is 0.42. So we just divide by the rotational inertia. That will give us the angular acceleration.